So it's my pleasure to introduce Yejin Choi, who's an associate professor at the University of Washington and also a senior research manager at AI2. She's done a number of really interesting research projects over the year. It's always fun to watch what Yejin's been doing, including things about common sense knowledge or language generation, and more recently about AI for social good. And she's had a number of really impressive accolades, including like the top 10 to watch in 2015 from IEEE's AI and recipient of the MAR Prize in ICCV, and also a member of the team that won the Alexa Prize Challenge in 2017. So lots of amazing things to watch for. So, well, that's probably enough.
Okay.
Looking forward to hearing what you say.
All right. So speaking of Alexa Prize Challenge, I'll start by sharing brief experience with this. So the goal of this challenge was to create conversational AI that can make a coherent and engaging conversation with humans. And the good news is that the team that I was part of, thanks to the amazing students, we won the competition, and it felt great to be the winner. The bad news is that conversational AI remains to be more or less unsolved. So especially, to our surprise, or not a surprising factor at all, is that the winning recipe was not based on neural networks with brute force more data, deeper networks, and spiked with reinforcement learning. That just didn't work. So now that's curious. Why would that be? Because we thought that neural networks do amazing things like superhuman performance on object recognition or image captioning. A lot of industry replacing their long-standing statistical machine translation systems with neural models. And then, of course, spatial recognition has been working really well. And even more recently, human-level performance on reading comprehension. Wow. And all these are based on very large amount of training data and then sufficiently deep networks. So this should work. However, if we look at closely, there are significant performance gaps across different types of tasks. So first of all, nobody is really reporting on superhuman performance on making a conversation or summarizing a document or composing an email on behalf of me or identifying fake news, despite the fact that we have a lot of data for all of this, or if not me, at least companies do have a lot of data for any of this. And they do have a lot of GPUs too. So why is it that we don't hear about this from the news? And even for those applications for which neural networks do perform at superhuman level for some data sets, they usually are not very robust if given unfamiliar, out-of-domain, or adversarial example, as Jonathan was talking about this morning. So what's going on here? I'm going to argue that, in fact, that's because there are very fundamentally two different types of applications out there. And we are primarily seeing the advancements for type 1 type task where shallow understanding can get you quite far. So an example is translating bananas are green in English sentence into a Polish sentence, banany są zielone. For this, neural networks are very good at learning word level or phrase level pattern matching so that it can learn to translate from one language to the other without really understanding much about a particular language. Whereas if I were to make a conversation and tell you bananas are green, you might tell me, no, they're not, or you might tell me they're not ripe. And if we try to learn the mapping function between input-output pairings this way, there's only a very weak alignment between the input and output. And in fact, we need some sort of abstraction, cognition, or reasoning in order to really know what to say next. And so which in turn requires knowledge, especially common sense knowledge. And ignoring this factor altogether and try to learn this mapping function just doesn't make a lot of sense. So to make another point about how important it is to be able to read between the lines, and let's think about news headline, cheeseburger stabbing. If you give this to state-of-the-art parser today, it's going to tell you that cheeseburger is a noun modifying another word, stabbing, which may be a noun or a verb depending on which parser you use, but doesn't matter. The fact that one word modifying the other doesn't tell us whether it means someone stepped a cheeseburger, or a cheeseburger stepped someone, or a cheeseburger stepped another cheeseburger, and so forth. And you know what may have been the actual meaning of this news headline, because you're able to fill in this missing information from the sentence, so that there are probably two people involved in this act, even though they were not even mentioned in the original news headline. And when we do that, it's the common sense knowledge that we rely on, especially physical common sense, is that it's not possible to step somebody using a cheeseburger because it's too soft, and stepping someone is not good, and it's immoral, so it's more likely to be newsworthy. Whereas if you step a cheeseburger, who cares? So when we look at and think about different types of knowledge, in fact, there has been tremendous amount of research for learning and extracting encyclopedic knowledge, like who is the president of which country and born in what year. But not knowing this, I can make a fairly okay conversation. However, it's really common sense knowledge that we need in order to make an okay conversation. So these naive physics type knowledge or social norms have not been studied very much. And if you look up ASL anthology, so this is, as we all know, the repository of NLP papers, most papers that dare to mention the word common sense are either from 80s or from the past few years. So nothing in between, complete void. And I think it's in part because there was a tremendous failure with the common sense in the 80s. And so, but recently it seems that people start to forgetting about the past failure. So there's been a few very interesting data sets, one of which from Microsoft as well, the Rockstory Common Sense data set. And so for all of these tasks, basically just brute force, more data, larger networks don't really go very far, and we somehow need a different game plan. So to be honest, I don't really know what that should be, but for lack of any better idea, I'm going to talk about two different directions. Thinking about neural network architectures that can better model the latent process in our mind when understanding and reasoning about text, abstracting away from the surface patterns. And then simultaneously, we might want to think more about representation formalisms, orthogonal to neural networks, and really think about how can we possibly organize and learn common sense knowledge using language as scaffoldings. Now, usually in this spectrum, I talk about these three pieces shown here, but the second one will be described by Antoine today. So I'm going to only give you a teaser for that and instead talk about dynamic entities in neural language models. So let's begin with the first part. So neural checklist model was originally designed to think about particular kind of language generation challenge. In particular, there are three different types of generation setting. Case one is a small input, small output, like machine translation. Case two is a big input, small output, like document summarization. And these two cases have been studied a lot more in the past. Whereas case three is the case when there may be only very sketchy input, small input, and then suddenly we have to generate bigger output. And for this, there are two unique challenges. There's an information gap. So the machine has to have a creative power to fill in a lot of information that was not even quite in the input. And then the second challenge is that the moment you start generating more than one sentence, it's very, very easy to make problems. So coherence becomes a big challenge as well. So a little bit more formally, the task that we're going to think about momentarily is that there's going to be an input, which is a title, and an agenda, which is a list of items that you want to talk about. And then the output will be a paragraph or a document with multiple sentences that tries to achieve the goal implied by the title and then tries to make use of only and all of the agenda items. And for now, we are going to use recipe generation as a running task, running example, but later the model will be applied to this dialogue response generation as well. So at the beginning, we thought that in order to generate recipe, we should first parse it, because that's what a lot of people do in NLP. Once we parse it, we are going to abstract away some prototypical graph structure out of it, from which perhaps we can sample a graph, which is like planning, and then convert that graph down to raw text. So that was our original plan, and we even worked on the first segment and managed to write a paper about parsing recipes into action graphs. But then we realized that doing this entire cycle is quite hard, because errors start propagating. It was really unclear what to do with this. I'm still wanting to do this, but in the meanwhile, we were wondering whether we could somehow simplify the whole process. And that's when we heard about encoder-decoder architecture in neural network literature, which apparently worked great for a lot of tasks, like machine translation. So let's encode the recipe title into a vector and then decode the entire recipe out and see what happens. Sausage sandwiches. So this is what happens. All right. I picked on purpose worse example. However, recurrent neural networks tend to repeat itself a lot, like sandwich. Eventually, it overcomes the sandwich overdose, but still, things must be repeated at least twice. So why does this not work very well for us when it does really well for a lot of other tasks? Well, it doesn't work well when there's only a very weak alignment between the input and the output. That's what I was trying to tell you earlier about different input-output comparisons. In this particular task, only 6 to 10% of words in the output came from the input, which means 90 to 94% of the time, output came out of nothing almost, or it looks almost that way for the neural networks or encoder-decoder architecture. So the rest has to come from somewhere else, and neural network, the off-the-shelf models don't operate very well. So with this in mind, the high-level idea is that is it possible to compose a neural network architecture that could sort of have this mental map of different items that you might want to check as you go. So that's what we did with the neural checklist model. But since this one is a little bit hard to stare at, let's look at a much simplified version as follows. So we're going to make garlic tomato salsa based on this visualization where we encode the title into a vector. There's a checklist that has a list of agenda items. And then at each time step, this is one unit of some recurrent neural network. In our case, it's a GRU, but that particular choice doesn't matter. So internally, it's going to make this three-way decision whether I am about to generate a word that is non-ingredient word or new ingredient word or none of the above. So let's just see how it works. So let's just say so far we generated the chopped up. Internally, the model is going to look at its own context and decide that, oh, it's time to use one of the new items. So it's going to do softmax over all the new items. And then let's just say tomatoes got the highest score. So we check that off from the checklist and move forward. So the second sentence might start with dice the, and at this point, the network might internally decide that, oh, let's use another unused item and softmax or do the probability projection only over the unused part, and let's just say onions were the second best choice, and check that off from the checklist and move forward. Now, something interesting is about to happen. So add 2. At this point, contextually, it's the moment when you go back to one of the already introduced items. That's just how the discourse cues are indicating to us. And that's also what the network picks up as well. So add 2, what should we use between tomatoes and onions?
Tomatoes.
tomatoes, because that's what was introduced earlier on, and the discourse convention is that that's what we do mention, and the network learns to do that. So, in fact, all this checklist is probabilistic, or at least it's not black and white, so it's based on the accumulation of attention scores, which reflects how much the model thinks that it made use of a particular ingredient. And then the three-way classification is also soft in the sense it's an interpolation of 3 different language model-like components, where the first one is generic language model, like RNNs or GRUs or LSTMs, whereas the other 2 are based on attention mechanisms, looking at either used portion or unused portion of the agenda item. So we did comparisons automatically, and of course the story is that we do better than other baselines, but so we borrowed machine translation measures, and when you just look at this number, it looks really very low. So you probably want to see actual samples, so I'm going to show you that. But briefly, this one shows what fraction of agenda items the model is making use of, and the regular encoder-decoder architecture with or without attentions practically ignores what's given in the input, because they are not very, when the input-output alignment is so weak, they're not very good at actually learning the mapping. So mostly they're ignored, whereas checklist can make use of much bigger portion. So example, skillet chicken rice. Baseline, that's regular RNNs. In a large skillet, brown chicken in oil. Add chicken and rice, cook. Add more rice and broth and cook some more, and so forth. So start in more rice, keep cooking. And probably it's edible, safe to eat in the end, but somehow there's not much of a coherence. So checklist, on the other hand, does much better job. So in a large skillet, heat rice and onion, add carrots and mushrooms, cook, stirs constantly until hot and bubbly, stir in seasonings, cook some more, stir in chicken, and then cook some more, and then serve over rice. So overall, the coherence suddenly became much better, even though in this model, we are not even doing any fancy modeling of discourse in any measure, but it was only this checklist that is external memory structure that allows recurrent neural networks to better manage what's happening in the long-term context. And that's going to be sort of a repeating message in the first half of this talk. So works really well when the input is familiar, and apparently skillet chicken rice is quite a common recipe in the data set. So, and this is a human recipe. It's probably a little bit better. So let's look at the failure case. Chocolate covered potato chips. Now, never heard of this before. And baseline, preheat oven, probably good idea, but then grease, flour, a pan, start baking it right away. So, because input is unfamiliar, it doesn't know what to do with this, just ignore it. In the case of checklist, it's paying more attention. It also does weird thing, like suddenly bake something right away, but then it realized, oh, I haven't done anything with chocolate, so let's melt it. And then it says silly things like add the potato mixture to the potato mixture, which is grammatically correct. It's just a little bit silly. Eventually, it's going to fry that in a hot oil, and I don't think it's a good idea to fry something covered in melted chocolate. So that says something about AI safety. And I'm not joking here. So the fundamental problem with neural networks today, despite all these amazing results, is that they struggle for unfamiliar input. And as a result, we cannot really trust them. So human recipe is much better. And I'm going to come back to this point in a bit. But let me very briefly mention how the same model was able to achieve better performance on a particular dialogue response data set as well. So moving on to the teaser of the neural process networks, which I'm going to only give you a motivation for. So this is another example globally coherent, deep fried cauliflower, that was the title. And then neural checklist model generated the following. Wash and dry the cauliflower. Heat the oil in the skillet and fry the sauce until they are golden brown. Drain on paper towels, add the sauce to the sauce and mix well, serve hot or cold. What's wrong with this? What? Huh? Yeah, cauliflower is still, it's clean, but hasn't been cooked yet. So again, I guess cauliflower is okay to eat raw, but so when I gave this talk about neural checklist model at Harvard University, a student asked me after the talk, are RNNs a mouth without a brain? And I wasn't sure how to respond to that. I guess I sort of agreed with her. So we need common sense knowledge to reason about these sort of unfamiliar situations. And humans can still do the right thing, whereas we don't know what machines will do, neural networks will do. So that's sort of the motivation. Like, can we think about new architecture that could read between the lines and reason about the unspoken but obvious facts? Like, for example, fry tofu in the pan. We know, just common sense-wise, we know that then location of tofu must be in the pan and temperature of tofu must become hot, even though the sentence doesn't say any of this. So in a way, it's similar to how we might be able to do mental simulation about a lot of things when we understand the stories and understand others when making conversation with them. And in fact, there have been some literature in cognitive science or psychology that that's what humans seem to be doing. Exactly how is always debatable, but we seem to be doing something like this. And so can we then challenge ourselves by asking this question instead of this question? So a lot of NLP research has been based on labeling. Let's label every word in a sentence with the syntactic and semantic categories. And that has been really very useful, but it focuses by and large on what is said in a sentence. Can we also think about, in addition to that, simulating the causal effects that's obvious but not spoken, and abstracting away from the surface strings? And in fact, there have been some recent efforts of that flavor, but of course, when people writing papers at the beginning, no paper will solve anything completely. So we have another one coming up, neural process network. You can hear more about this in a bit today, but I will leave it there and then talk about the next component, dynamic entities in neural language models. So that's work with other colleagues at UW. Noah was here as well today. So the problem with neural networks, this is another sample that I found from a paper that introduced the Lambda data set, I think. So human says, what's your job? Machine says, I'm a lawyer. Human says, what do you do? Now machine says, I'm a doctor too. So, I mean, somewhat understandable if you think about how I embedding here and I embedding here. When it starts with a word embedding, it's starting like the same word. It's the same word. And so Jane in Jane Eyre may be the same as Jane in Mentalist in terms of how they start with neural representation. And then when I say she to mean Jane, now suddenly they kind of look like different words. In addition to that, there's this philosophical question of, is it possible to encode very large context into one vector? And Ray said, no, it's not possible. I don't know, maybe some of you in the audience who are very, very young may have not known about this, but he said that. And I'm going to just repeat what he said by adding that nor into a sequence of vectors. It's just not enough. So recurrent language model has a sequence of vectors, basically. And our model is to add more external memory that can have a better long-term representation as follows. So let's just say this word is some entity. And then I'm going to create this separate memory chain, which is also recurrent for some time. And whenever I see a new entity mentioned, I'm going to create a new chain and they are going to be just copying themselves over time until there's a co-reference to the same blue entity, at which point I'm going to now combine the context coming from the recurrent neural network with whatever I was storing here as a separate memory chain, and so forth. So that's the gist of this model, that let's have a separate chain in which we store a little bit more precise information about different entity mentions corresponding to the same entity. And in doing so, we are now sort of having recurrent entity model in addition to the recurrent language model. And whenever we need to compute new entity embedding in this chain, we are going to interpolate that between whatever was coming from the neural network language model part and then whatever was stored here. And that interpolation is based on gating. So that's a fairly standard thing to do. And the gating can be parameterized in many different ways. This is a particular way of parameterizing it, but doesn't have to be this way. So once we have that, then what can we do with this? Well, usually when you sample words out, it goes in sequence in the language model part like this. And when we do that, instead of conditioning on just the hidden state of the recurrent neural network part, now we can condition also on whatever is relevant entity for that part. By doing so, we just have more precise conditioning on the context that is more relevant than how it would have been possible otherwise. So it's just, in some sense, I mean, like feed-forward neural network with the 2 layers should be able to approximate anything in theory, but nobody can train it to do anything useful. And that's why in the computer vision community, we've been seeing a lot of new architectures like residual net, dense net, condensed net, and so forth. So similarly, I think we need to do more research like this. This may not be the best architecture yet, but the kind of architecture that allows us to carry on long-term context more precisely. So that's a sort of the intuition. I'm going to give you just a very brief intuition about what we do for training and testing. So we went with this idea of a generative model, such that for each word there are a bunch of bookkeeping variables that we create, such as a Boolean variable that asks whether I'm currently an entity, part of an entity or not. And if so, which entity am I belong to? Do I belong to? And then what's the length? And there's this length that decreases over time until it hits 0. It's one way to do that. There may be different ways of doing it. And finally, coreference relations. And this one just shows how these variables might refer to different information. So during training, we are going to, in this work, we'll just assume that we have this perfect coref chain that was given from the sky. That's probably an unrealistic assumption to make, but as a first step, that's what we did. And then during testing, of course, it seemed a little bit less cautious to assume that for testing, so we just sample and marginalize them out using importance sampling. And by doing this, then what can we do? We can then think about different use cases. So we first of all looked at just using this as a language model that may be able to marginalize out different types of coreference decisions, and then in that case, it can lower the perplexity on the Cornell test set. And then in the second case, we also used this in order to improve a certain coreference resolution system that we could piggyback on by adding our scores, the model scores as additional scores to help with the ranking. So we plugged our system to ranking-based system, and we were able to improve the performance. It's not state-of-the-art because people keep improving on this quite a bit, and our colleague at UW, Luke, has much stronger results now. And then finally, there was also a very interesting new data set that was a little bit common sense inspired, and it was about predicting what entity may get mentioned next. And for that task also, we were able to perform much better than other strong baselines. So that's another story that sort of repeats this theme of, or spirit of, having new neural network architecture that might better represent the latent process that goes in the way text is written or text is understood. And then now I'm going to switch the gear quite a bit and talk about this verb physics, which is more on this side. So this work is sort of motivated by this hope that in the future we may have a home robot that should understand a lot about different household items so that it can interact with them. It should have understanding about relative size, weight, rigidity, strength, and so forth. So it's good to be aware that usually people are larger than a chair. And if I were to look this up on Google, nobody says this. But now I said that, so you can search this. But when I searched it for the first time, I couldn't search that or any of this. Because nobody says any of this. It's trivially true. So this is a known fact as a reporting bias, that people don't state the obvious. And then when finally people say something, it's like exceptional case. So we must now conclude that horses are similar in size to dogs. So then what do? I thought that the answer must be in computer vision. Let's look at images. So we worked on this, and one of the papers looked at lots of images and estimated relative size differences, adjusted with depth differences. And then we were able to learn some knowledge, like dogs are usually bigger than cats. But the takeaway from this work was that I thought NLP is very hard, but computer vision is also hard. And in addition to that, computer vision just takes more computation because images are bigger to process. So after processing lots of images, I only got like hundreds of knowledge nuggets, which seemed kind of small. And then in addition to that, size we can measure, but what about relative weight or strength differences or speed differences? And these are visual to human eyes, not really for computer vision yet. To some degree, yes, but not in a reliable way that I could depend on. So our revised plan then is that, one could just wait, but since we don't have anything better to do, let's go back to language, but with a different plan. So key insight is this. Even though nobody says any of this, people do say that they throw a pen or stone, chair, and so forth. So all of these are possible when the agent is typically bigger than the object, heavier than the object. As a result, the object is moving faster than the agent temporarily. So the representation, which we named as verb physics, goes as follows. It's very similar to semantic frames, frame semantics, but it now talks a little bit more about pragmatic meanings of language. So for any pair of potential arguments of a predicate, we can think about what may be implied. So we walked into the house may imply that I am probably smaller than my house and lighter than my house and moves faster than my house. And if I squash a bug with my boot, probably my boot is, X with Y. Squash the bug with my boot, then the bug is smaller than my boot and lighter than my boot and so forth. So there are this sort of a long list of obviously likely truth about the world that comes to our mind, and perhaps we can learn to detect that as well. So in terms of model, we decided that perhaps we can solve two related problems simultaneously, in particular, physical properties implied by verbs. So what kind of actions do imply about different arguments? And then also, in general, different relative knowledge in between objects. Across 5 different attributes in this work, although one can extend it to include other attributes as well. And if you've been waiting for deep learning to pass, so in this work, we didn't use deep learning per se, although we did make use of neural embeddings. But otherwise, it's a factor graph with lots of variables that have probabilistic interpretations. So it goes something like that. I'm going to give you a very sketch idea of what we are doing. So we are going to throw in a bunch of random variables. That might mean that for each of them, it might mean something like P is either bigger or smaller or comparable to Q in terms of size. So they can have these 3 different value assignments. And then on the other side of the graph, we can also throw in a bunch of random variables that encode action implications. Again, the value can be either bigger or smaller or same. And then they can be about a particular predicate like throw with respect to a particular attribute like size. In fact, this predicate variable is a collection of random variables internally due to the fact that using the same verb like throw, we can use in many different frames. So we just use different random variables for different instantiation of any particular predicate. But for now, we might just assume that they're sort of like behaving similarly. Now, at this point, though, there's no evidence about any of these random variables' truth assignment because nobody says my house is bigger than me, and nobody says when I throw something, I am usually bigger than the object. No one says any of this. So the only thing that we do observe from language is how people use different arguments together with different actions. That, for example, I threw my bag as I walked into my house. So people do say this, and that's the relational evidence is the only evidence that we do have. So sort of translating this intuition into the graph model is that we are throwing in potential function that quantifies the selection of preference between a verb and its arguments. And then similarly, a lot of potential functions for object-object similarity, as well as verb-verb similarity, as well as frame-frame similarity. And then finally, we cannot suddenly decode knowledge out of nothing. So there's a little bit of seed knowledge given as unary potential function so that we can reason about the entire network. And so far, we've been only talking about size, but we can keep doing this until the network gets very, very messy by adding this weight part and other part as well. So there's this well-known inference algorithm known as loopy-belief propagation. That's what we did for making the inference. And the conclusion, very briefly, is that the random assignment would be 1/3 accuracy. Majority baseline would be about 44 to 50. Whereas if we just use neural embeddings to reason about different knowledge without the entire graph, but just one node independently from all the other, then that's how much we do. And then having this graph inference can help improving the performance further. And on one side, we are looking at frame predictions. On the other side, we are looking at object-object knowledge. So to summarize, we have explored whether it's possible to reverse engineer naive physics type knowledge from language, even though people don't speak the obvious facts, but perhaps we can design a model or inference algorithm that could still be able to reason about unspoken, but what we all assume with each other which systematically influence the way people use language, which then give us some clue about what may be true about the world. And we can do this without having robots that can have an embodiment and interact with the world. All right, so now I'm going to conclude with some remarks about what future research directions we might pursue further. So as far as neural network architecture, there have been some debates about whether there should be innate architecture or not. I'm obviously on the side of having innate architecture. I think in the NLP community, there have been more emphasis, relatively speaking, more emphasis on the linguistic sentential structure, where there usually are some explicit structure, and it's very, very well studied, whereas the moment we start thinking about document level or discourse level or just generally long-term context or latent processes of how the world works, things become much less clear how to handle this. Nonetheless, I think this part is very important to pursue further. And then as far as formalism, I think we should really start thinking more about like what to do with the common sense. I was told not to use the word for some time. And I think it's because it was major failure before, but I realized at some point that it's just nonsense to conclude that that direction is going to be forever impossible when the past failures were based on weak computing power, not much data, no crowdsourcing, and not much computational, as strong computational models. And also it was done by non-NLP people, and I think with language we can do a better job. Or we should try before concluding that it's not going to work. So in terms of physical common sense, the potential impact cases could be more with zero-shot, few-shot reasoning cases, especially when there's language and vision and robotics applications. But we can also do similar things with the social common sense, which I haven't talked about today. However, we've been working something along this line with connotation frames, and also we now have a new ASL paper coming up, which I'm going to give you a teaser about. So it's going to be about, based on the rock stories developed at Microsoft and Rochester, where the story goes like this. The band instructor told the band to start playing. He often stopped the music when players were off tone. They grew tired, started playing worse after a while, and so forth. So when there are these sort of people involved in a story, we can oftentimes reason about what people might feel. Like here, the instructor was furious and threw his chair. It doesn't say what these guys feel now about that situation, but we can imagine that they must feel fear or feel angry or sad, even though it's not mentioned here. So we can sort of have this annotation, very low-level annotation about what people might feel, what people's motivation might be before and after different actions and events. And we have a bunch of new annotations and baseline models reported coming up soon. And then related work also in ACL will be about common sense inference. For example, if someone cooks Thanksgiving dinner, probably that person's intent is to impress their family. Afterwards, maybe they will feel tired, but still feel a sense of belonging. And finally, other people, even though they are not mentioned in the sentence, they will probably feel impressed or happy and so forth. So we can reason about what people might typically do before and after in terms of their mental states. So it's also coming up at ACL with a bunch of new data set. So finally, I would like to also add that this new modeling power does create us some new opportunities for doing more human-centric applications so that people don't fear just AI as a negative, potentially scary thing. I think we could try doing more positive acts in that space. Personally, I think we should work more on interactive AI because that's what robotics people really want as well. And especially with the neural network, it seems that we can do a lot of creative things in text generation too. So I will just read in this sonnet that was generated by a machine. So Turing was the title, and it goes like this. Creating some electric slot machine of hearing those familiar voices say, awake behind an empty picture mean, the windows open over Alan Kay. Consider me of regular expression, or maybe something very quickly typed. And I forget about an old obsession, 100,000 people getting hyped. Become the biggest part of my computer and take another journey down the road, or set up balance on a minor scooter, or even better, whose Enigma code and music takes control of all the means, surrounded by a world of strange machines. Couldn't fool anybody yet. Thank you.
Thanks very much for an awesome talk, Yejin. We have about 5 minutes for questions, so maybe I'll run a mic.
I had a question. I wanted to know your thoughts on, so back in, I guess, previous, there was work done for OpenPsych, or the psych knowledge base, which was to encode common sense knowledge in a knowledge graph. And I was wondering about your thoughts on the utility of using that for possibly distant learning.
Right. So I think there have been some couple archive papers that I tried to use at least ConceptNet, which is maybe analogous to OpenPsych, and try to see whether it can improve some downstream applications like QA and entailment and the dialogues. So it's a great question. Personally, I didn't look at OpenPsych, but I heard from other people who did look at that it's very much is a hierarchy, so it's a very dictionary knowledge or taxonomy knowledge. ConceptNet, which I did look myself, is also very taxonomic knowledge, or predominantly that. They do have a lot of other relations that I really appreciate and find very interesting. Unfortunately, coverage on those more interesting cases are a little bit lacking. So, which sort of motivates our new data set that tries to cover, like motivation is, for example, included in the ConceptNet relation definition. However, the coverage is relatively small, and so it's one way to increase the coverage. Eventually, it may be useful, but we'll have to find out.
So this is supervised learning using human annotated like data that, and is the hope that you can use this with the correct architecture to create, to help the system to be able to, in general, understand how to make these type of inferences?
Yes. So what we do show in the paper is by using very encoder-decoder architecture, basically almost that, we can learn to encode any textual description of an event and then reason about what might happen to people's mental state, such that given a previously unseen event description in the test data set, it can still reason about what's likely mental state, which is what we basically have to be able to do. And if we are using old-fashioned logic-based systems, then that wouldn't work. Then there has to be knowledge populated for everything, whereas with neural network, we can learn to compose the likely anticipation instead of having to crowdsource literally all of it, which I think is just not possible.
Maybe we have time for one more quick question before the end of the session.
So how do you know that when you're done? As in, how do you measure coverage or recall? Like you can measure precision, but what about recall?
So in this particular work, we have a sort of like test set cases where test set starts with this left-hand side of the logic, and then we try to predict the right-hand side. But I wouldn't be able to say in terms of like recall with respect to everything that I ever know of. I wouldn't know yet. Maybe if we start thinking about it, someone will come up with a number. But
Thanks once again, Yejin.